Okay, sorry about the technical difficulties. I'm seriously getting tired of getting kicked out of Zoom. So my my tablet is freezing on me. I think it's getting too hot, but I bought a cooling pad for it. It's not really even working. I'm definitely going to call Microsoft when I'm done with this class today. So see if I can give them back their computer and get something better. Okay, let me reshare my screen and continue where we left off. Okay, I was just proving that, okay, for P series, okay, I don't want to get too much into it. Okay, I'm certainly not going to use any external calculator or anything to do this, but I kind of want to see what this looks like. Okay. Okay, so yeah, this is 1 over the square root of x, okay, 1 to infinity. And the deal here is that what does the 1 over the square root of x look like? Well, it looks like this. That's what it looks like. Okay, that's 1 over the square root of x. The problem is that what this is saying is it's saying that this area under the curve is equal to -2, which is completely wrong. Okay, this is wrong. Okay, so what we can conclude is that it is not equal to -2, which means that this fails. If it's a negative, if it's a positive, it works. If it's a negative, it does not work, and so we just say that it is divergent. It then becomes divergent. The other way that we can see this, okay, is that again, if we have the integral 1 to infinity of 1 over x to the p dx is equal to 1 over, well, let's go back to the limit. The limit as x goes to infinity, no, t goes to infinity, sorry. T goes to infinity of, and we said this was 1 over p minus 1 times t to the p minus 1. Was it p minus 1 or 1 minus p? It was 1 minus p, I think. T to the, no, it was t to the p minus 1. But it was 1 over. T to the p minus 1, right, and then minus 1. Okay, and we said that if p is bigger than 1, then this exponent is positive. Okay, then the exponent p minus 1 is greater than 0. Okay, and so if we take the infinity here, okay, then this becomes 1 over t to an infinite. I'll put positive infinity, okay, which is 0. That goes to 0. Okay, that goes to 0. The limit as t goes to infinity. Okay, positive infinity. Okay, the other thing though is what happens when it's smaller than 1. Well, then this thing becomes, think of p being a negative number, right? Let's think of p as smaller one. Then if p is less than 1, then p minus 1 is a negative number, right? So then it's a negative number. So this is negative. So what is t to a negative exponent? Right, 1 over t to a negative exponent. We'll just say that this is negative c. Okay, let's just say that c is equal to p minus 1. But it's negative, right? It's a negative number, right? So it's negative, okay, it's negative c. Okay, how do I know it's a negative c value? Well, because it's less than 0. And so this becomes t to the positive c, right? And then we're going to say, oh, well, what's infinity to some value? Well, it's infinity. Okay, infinity raised to some power is still infinity. And so this really becomes, this thing, instead of going to 0, okay, this thing now goes to infinity if it's a negative value. If p is a negative value, or if p minus 1 is a negative value, then this thing goes to infinity and it diverges. Okay, so the thing diverges. So either way, okay, the summation of n equals 1 to infinity of 1 over x to the p, or n to the p, sorry, 1 over n to the p, okay, is convergent if p is greater than 1, and it's divergent if p equals 1, but it's also divergent if p is less than 1. If p equals 1, then it's a harmonic. When we proved that diverged. And if it's less than 1, well, it's still going to diverge. Okay, so there we go. Okay. Okay, and so this is called the p-series test. Okay, p-series test. Okay, so we can just look at the p-series and we say, ha, I know if it converges or diverges based on what it is. Okay, for example, let's use the p-series test, okay, on this guy. Is the series, okay, summation n equals 1 to infinity of 1 over n cubed convergent or divergent? Okay. Okay, well, is the series convergent or divergent? Well, let's see. Let's see what we got here. Okay. So p is equal to 3, which is greater than 1. So by the p-series test, okay, so by the p-series test, it is convergent. Okay, we already talked about the harmonic series. Okay, so let's do an integral test on a harmonic series. Okay, let's do the integral test. Okay, so number 3 here. Test for convergence of the summation of n equals 1 to infinity of 1 over n. Okay, and we're going to say, hey, well, we already know what this is. This thing diverges. But let's do an integral test on this one real quick. Okay, so the integral from 1 to infinity of 1 over x dx. Oh, okay. So let's see, is this thing going to converge or diverge? Well, what's the integral of 1 over x? What's the integral of 1 over x? So this is the limit as t goes to infinity of 1 to t of 1 over x dx. Well, the integral of 1 over x is natural log. Okay. This is the limit as t goes to infinity of 1 to t, or sorry, this is going to be of natural log of x from 1 to t. Okay. The limit as t goes to infinity of the natural log of t minus the natural log of 1. Okay, so the natural log of 1, that goes to 0. And what does the natural log of t look like? Well, natural log of t goes like that with respect to t. Okay, and so as t goes to infinity, what happens to the natural log of t? Well, it also goes to infinity. Okay, so this diverges. But we already knew that. Well, how do we know that? Because it's the harmonic series. So this is just another proof that the harmonic series, which is a p series n equal to 1, right? So the harmonic series, which is a p series n equal to 1, diverges. Okay, so we've done it two different ways. We've shown that this thing diverges. We did an algebraic proof yesterday, and today we did a proof by integral test. Okay, number 3. Okay. Okay, number 3 is determine if the series summation n equals 1 to infinity of natural log n over n converges or diverges. We don't know what the sum converges or diverges to. We're just going to see whether or not it does. Okay, we don't know necessarily what the limit is of this thing. Okay, of the sum. Okay, but we just want to know, does it converge or diverge? Okay, we just want to know the nature of it. So let's use the integral test. Integral of 1 to infinity, natural log x over x dx. Let's do a u sub. U is equal to natural log x equals 1 over x dx. Here's my 1 over x dx right here. That's my du. Okay. So I'm going to go 1 to infinity. No, 1 to infinity. Is it 1 to infinity? No, I think it's 0 to infinity. Because u is equal to the natural log of x. So this is 0 to infinity now. Okay. Nice. If I change the limits of integration to u, you know what? I don't want to do that. I'm going to change everything back to x so I don't have to change the limits, because I want to keep the limits the same. I don't want to go to 0 because that might make things go to infinity when I don't want them to. Okay, so let's see what we get here. So this is just going to be the integral of u du. Oh, okay. That's the integral u du. Okay, so what is that? The integral, that's u squared over 2. Okay, that's u squared over 2. Okay, but I would have to evaluate this with respect to u, but I don't want to evaluate with respect to u, so I'm going to plug in this natural log of x. I'm going to go natural log of x squared over 2, now evaluated from 1 to t of the limit as t goes to infinity. Okay, so I would have put the limits of integration as 1 to infinity, but we really can't do that. We have to use that dummy variable t to plug in so we can actually take a limit of this thing. Okay. So what does this thing become? Well, this becomes the limit as t goes to infinity Did you pause? Bro, did you pause? I paused. Yes, I paused because my battery died. So I should be, am I back again? Am I live? I'm good. Okay, good. Oh my gosh, this has been, should we just call it a day at this point? Honestly, whatever. Okay. Just kidding. Okay, so, no, got calculus to do. Okay, the limit as t goes to infinity, okay, of natural log of t squared over 2 minus the natural log of 1 squared over 2. Well, this thing again goes to 0. Okay, and what's the, if I plug in infinity here, what's the natural log of infinity? Well, it's just infinity. This thing goes to infinity. And then infinity squared, it's just infinity. Infinity squared divided by 2, that's still infinity. So this thing goes to infinity. Okay, and so we say that it diverges. Diverges. This thing diverges. Okay, therefore, okay, since the integral 1 to infinity of the natural log of x over x dx diverges, then the original series diverges. Then the summation n equals 1 to infinity of natural log n over n, okay, also diverges. It also diverges. Okay. The remainder estimate. What is going on here? Oh, that's wrong. Yep. Again. Plug it in so my battery does not die. There we go. Blah, 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 blah. Whatever. Okay. Also diverges. Something is messing with this thing. There. Okay. Okay, remainder estimate, remainder estimate for the integral test. Okay, remainder estimate for the integral test. Okay, suppose, okay, f of k is equal to a sub k, where f is a continuous positive decreasing function positive decreasing function for x greater than or equal to n, and the summation of a sub n is convergent. Okay, so we get a value, okay, it's convergent. If r sub n is equal to s minus s sub n, okay, then the remainder here, r sub n, we'll call this the remainder, is sandwiched between two items. Sandwiched between two items. This is sandwiched between n plus 1. The next integral, okay, the next integral n plus 1 f of x dx and n f of x dx, okay? Sandwich between those two. So it's just saying, okay, so say that we look at our s sub n's here, right? So we've got s sub n's converging, okay? So these are our cumulative sums. S sub n's are converging to some value, okay? And so the difference between our s sub n and our s, our limit, okay, that is the remainder, okay? That is called r sub n. Okay, that's the remainder of this. Come on, just work for me. There we go. The remainder is this value here, the error, basically, the error. Okay, and what we're saying is we're saying that that error, okay, if we look at the original function, this is the cumulative function, by the way. This error, okay, is sandwiched between two things. This error, s minus s sub n, okay, this is r sub n. This is sandwiched between two items. Now, let's look at the original function, okay? Maybe the original function looks like this. Okay, this converges. So this is a sub n, right? So this is, maybe I should have put that in a different color. Okay, so, okay, let's put this in a different color. Actually, let's go back. Okay. Oh my gosh, did it again. Whatever. Okay. Okay, so say that we have, right? Okay, these guys, right? And I keep adding just a little bit. So this is a sub n. Why is that guy so big? So big. A sub n, okay. And so for our sums, our first sum is just going to be our first number, right? It's going to be a sub n. Say that this is 1, right? Okay, and then what are we going to do? We're going to add another, we're going to keep adding these values, and that gives us our s sub n's. And what it's saying is, it's saying, look, if I'm here, right? And then I go to n plus 1, okay? This error, this remainder here at s sub n is sandwiched between the integral, okay, the integral up to n, okay? So there's an integral up to n, okay? That's a certain value, okay? That's going to be the, no, sorry, my bad. It's not 1. It's this one here. Come on, keep going. Keep going. You can do it. Yeah, I was right before. Okay, let me start this over because it's not making me happy. Okay, we've got this as our function, cumulative function. This is s. This is s sub n. That's good. I'm going to start this here. Okay, that's fine. Now I'm going to start my other dots. Okay, and they're going to go down slowly. Okay, the problem is that, you know, I really have to zoom in on this thing. but we're going to take n, and then we're going to take n plus 1. Okay, and we want to know what's the integral from n to infinity. Come on, dude. What's the integral from n to infinity? Okay. And then what's the integral from n plus 1 to infinity? Well, that would be, the n plus 1 is going to be less of an area. Okay. That's going to be less of, oh. Hello? Did it freeze again on me? No. Okay, good. I'm still talking. That's good. Okay, just allow me to draw. You can allow me to do anything? Oh my goodness. It says it's working offline. That's wonderful. Is it my internet that's a problem? I don't know. Probably. If it's not one thing, it's another. Come on. You can do it. You can do it. Whatever. It's good. Okay. How about if I choose insert or home or anything at all? Can I exit? Nope, can't exit. I'm stuck. How about if I just stop sharing? Let's stop sharing. And now let's see if I can do anything inside the app. Yeah, it looks good. I'm still gonna exit out of the app though. And then go back in. Duh, these technical issues are driving me insane. There we go. Okay, so let's go back to sharing my screen. Share. Okay, so the integral, turn this into the correct color, the integral from n to infinity, okay, is bigger, okay, for f of x dx, is bigger, this thing is bigger than the integral whoa, what the hell? Could you just bring my stuff back, please? Thank you. Oh, gosh. Okay. So the area from n to infinity, okay, is going to be bigger than the area from n plus 1 to infinity, okay, of f of x dx. Why? Because n plus 1 will start here and it will go to infinity, okay? Do you see how the blue region is smaller than the green region? Because the green includes the blue, therefore it would be bigger. So we're saying that, okay, that, move this over to, that the area here between S sub n, okay, which we're calling our remainder, S and S sub n, okay, that is bounded by the integral, okay, the integral, I want to color code this, the integral n to infinity of f of x dx and the integral, that's a bad integral, the integral n plus 1 to infinity of f of x. Okay, and this one is smaller because it contains less area. That's all it's saying. Okay, with that said, let's just do a problem. Okay, let's get out of theory hell here. Okay, let's just run some numbers. Okay, number 4. Let me close this out. Make it smaller. Where's my paper? Did I run out of paper as well? Is this not working for me? It must be Thursday. It must be like the end of the week. And I'm getting a little cranky at the things. Don't piss me off today. Okay, number 4. Okay, estimate error in approximating okay, n equals 1 to infinity of 1 over n cubed by taking S10 as its approximation. So we're going to take this S10. Okay, what does 1 over x cubed look like? Well, it looks like this. Okay, and so we're going to start at 1. 1 over 1 is 1, right? So we'll start at 1, 1. This is 1. This is 1. It doesn't look like it, but whatever. It's supposed to be a square. Who cares at this point? Okay, and so we want to estimate the error, okay, of this thing at S10 when n is equal to 10, right? But it's the sum of all of those values. Okay, it would be this. S10 would be what? Well, S10 would be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed. So it would be adding up all these values. Like this would be at 2, 1, 2. If we would add up all these values, and then at 3, right? And then we would add it at 4 all the way. Okay, maybe 5, 6. Okay, we're going to add up all these values until we get to 10. Okay, boom. Okay, add up all those values, and they're saying that that is going to be bounded by the area under this curve. Okay, from 10 to 11. 10 to infinity and 11 to infinity. Okay, so, okay, so we have 1 cubed, 2 cubed, 3 cubed, 1 over 4 cubed, 1 over 5 cubed, 1 over 6 cubed, 1 over 7 cubed, 1 over 8 cubed, 1 over 9 cubed, and 1 over 10 cubed. Boom. And I'm going to save you the work on this. I've already done the work for you on this. This equals, okay, this equals 1.1975. That was a good year. That was the year I was born, 1975. That's good. Okay, so 1 over 1975. Okay, and so what is this saying? This is saying that this is our approximation. We're asking how good of an approximation is this? What is the error on this thing? What is the error bound? Right? How close to the actual value, if I took this thing out to infinity, how close to the actual value would I get? What's the error bound on this? And we can say that the error bound is from 11 to infinity of 1 over x cubed dx, okay, is less than or equal to, okay, r of 10, that's the remainder, that's the difference between s and s10. This is s minus s10. Okay, that's the actual sum versus, okay, versus the approximated sum going out to 10 digits, 10 terms. This is less than or equal to, okay, and the integral from 10 to infinity of 1 over x cubed dx. Okay, so let's see what we get here. Let's do this one first, the upper bound, right? What's the error bound? we want to kind of know what's the biggest value that this thing can get. Okay, and that's the upper bound here. Okay, so we wanted an upper bound, okay, on our error. Let's say there is a lower bound on our error too, but the upper bound's a little bit more interesting to talk about. So 10 to infinity, okay, of x to the negative third power dx, okay. So what's this going to become? This is going to become x to the negative 2 over negative 2, right? And this is the limit, okay, as t goes to infinity from 10 to t, okay. Cool. Okay, so I'm going to rewrite this as the limit as t goes to infinity of 1 over negative 2x squared, okay, from 10 to t. Okay, so this is the limit as t goes to infinity of 1 over negative 2t minus 1 over negative 2 times 10 squared. Okay. Well, what's this thing going to go to? That thing's just going to go to 0. Why? Because it's just 1 over negative infinity, which is just 0. Okay, and so this is 0 minus a minus, so this is plus 1 over 2 times 10 squared, which is 200, which is 0.005. So the error is going to be bounded, so the error is at most 0.005. So again, it was 1.1975 was the sum, right? So the error on this is S minus S10 was equal to 1.1975, right? So that's sorry, that's not what that is. So S10 is this thing. The remainder, S minus S10, okay, is at most 0.005, at most 0.005. We could find a lower bound for the error too if we really wanted to. We would just have to change this to 11 instead of 10. Okay, and so that would give us, we'd do the exact same thing, and then that would give us 1 over 2 times the 11 squared. Okay, so similarly, okay, we would get this thing, 1 over x cubed dx, right? That would become this, which is 1 over 2 times 121, which is 242. So what's 1 over 242 real quick? 1 over 242, okay, is 0.004, okay, about 0.004. I'll say 0.004132. Okay, it's about that. Okay, so we know that, okay, so we know that we have 0.004132 is less than or equal to S minus S10. But what was S10? We calculated that to be approximately 1.1975, which is less than or equal to 0.005. Okay, so let's just add 1.1975 to both sides. This gives us an approximate region for us to look for our true sum. Okay, our true, what this thing is going to truly converge to. Gives us a ballpark to work with, 1975. We're going to add that, right? Boom. Okay, so we know that S is somewhere between, okay, 1.1975 plus the answer that I got. Okay, that's 1.201632 and 1.1975 This is going to be 1.1975 plus 0.005 is 1.2025. Now again, I don't know exactly what this thing converges to, but it converges to a value between, okay, between 1.2016, I'll just leave it there, and 1.2025. Okay, I don't know what it converges to, but I do know that it converges to a value. Okay. Okay. Let's go on to, that was a long 11.3. Let's go on to 11.4. Okay, and this is called the comparison test. Okay, comparison test. The comparison test. Okay. Okay, suppose summation, oh, that was weird. The summation of A sub n and the summation of B sub n, so these two series, are series with positive terms. Are series with positive terms. Okay, number one. If the summation of B sub n is convergent and B sub n is greater than or equal to A sub n for all n, okay, then A sub n is also convergent. Okay, and we talked a little bit about this when we talked about sequences. Now we're just putting it in terms of series. Summation of A sub n is also convergent. Okay, good picture here. Okay, is that we're saying that B sub n is convergent. B sub n is convergent. So, okay, so let's say that B sub n here is equal to 1 over x to the 4th power. Okay, and we're going to say that that's a P series that is convergent. It's going to converge. Boom. B sub n is there. And we're saying, look, A sub n is smaller than that for every single term. Okay, for all n, it's smaller. A sub n is smaller. So maybe A sub n is 1 over x to the 5th power. And we're like, oh, yeah, if I put, oh, it's not x, I'm sorry. These should be n's. Okay, n to the 5th power, right? So I start off with 1, that's just 1 over 1. They're the same. So they'll start at the same spot. Okay. Whoosh. 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 Okay, they'll start at the same spot. They'll start at 1, 1. But then what happens at 2? I get 1 over 16th for B sub n, but then I get 1 over 32 for A sub n, and A sub n is certainly smaller. And so what we're saying is, we're saying, look, if B sub n is always bigger, okay, if it is always bigger and it converges, then anything smaller than that is also going to converge. It's going to get it sandwiched. It's kind of like sandwiched between the two. Okay, so Okay, so this A sub n also converges. If B sub n converges, A sub n converges. Okay, so both converge. Okay, number two. Let's look at the opposite of that. Okay, if A sub n is divergent, and B sub n is always bigger than A sub n, and B sub n is still bigger than A sub n, okay, for all n. Okay, then B sub n does what? Then B sub n diverges as well. Because you got, again, a picture's worth 1,000 words, right? So we've got A sub n here. A sub n maybe looks like this. It diverges, right? Diverges. Okay, so maybe A sub n is equal to x squared. I don't know. Okay, that thing diverges. Whoosh. Okay, and then we have B sub n. Okay, B sub n. Let's use a different color here. Let's use black. Okay, B sub n goes like this. Okay, maybe B sub n is an exponential. I don't know. B sub n is equal to e to the x. Okay, whoosh, goes up really fast. Then what do we know? We know that if of all the terms of e, I keep using x's, I'm sorry. Okay. Okay, if all the values of E sub n are bigger than a divergent series, then wouldn't B sub n also be divergent? Then yeah, right? If A sub n diverges and B sub n is always bigger than A sub n, then that also diverges, causing it to diverge. Saying, look, bro, I'm going to infinity, you're always bigger than me, so you're going to infinity as well. So this thing always diverges, okay? Both diverge. Then the summation, okay, then the summation of B sub n also diverges. Diverges. Okay, and so these are divergent. Okay, both diverge. And this is the basis of the comparison test. We can compare two things. Okay, so number one, determine, okay, whether or not, or whether the series summation of 5 over 2n squared plus 4n plus 3, okay, n equals 1 to infinity, converges or diverges. Okay, determine whether this converges or diverges. Okay, cool. So what do I want to compare this to? What would I like to compare this thing to? Well, let's say that you know, that this is A sub n. A sub n is equal to 5 over 2n, or we could even put the summation here, okay, or whatever, I'm just going to call it A sub n. Okay, A sub n is equal to 5 times n squared plus 4n plus 3. And would you agree that this is less than or equal to, okay, less than or equal to, well, I'm gonna do a strict less than on this one, okay, that this guy is less than okay, less than 5 over 2n squared. We're going to call that b sub n for all n. Is this true? Is this true? If I add more value to the denominator, what does that cause that fraction to do? If I add extra terms here to the denominator, what does that add extra? What do those extra terms make this thing do? Which ones? Well, doesn't that make it smaller? If I make the denominator bigger, okay, it means that the whole fraction is smaller, right? If I divide by more value, these extra terms add more value onto it, right? Okay. Okay. But let's so this is true. This is true. This holds. This holds true. Okay. So that's good. So a sub n is always less than b sub n. Okay, it's always less than b sub n. Okay. Okay, that's good. That's good. That's good. Now, what can we say about this guy over here, b sub n? B sub n, the summation of b sub n for n equals 1 to infinity. Okay, let's look at b sub n here. The summation of n equals 1 to infinity of 5 halves n squared over n squared. That's going to be equal to the summation of n equals 1 to infinity of 5 halves times 1 over n squared. Now, does this thing converge or diverge? Does that thing converge or diverge? You got a 50-50 shot at this, right? It's 50-50 yes. Okay, does that converge or diverge? If you're a betting person, what would you place your bets on? Converge or diverge? Yep, there you go. It converges. Converges by the p-series test. Yeah, because why? Because remember, there was a theorem at the very end of the very last line of our notes yesterday was that, right, if a sub n converges, then so does c a sub n, right? So if a sub n converges, then so does c a sub n. Putting a constant in front of here doesn't change anything. So this thing, 1 over n squared, converges by the p-series test. By p-series test. Okay. So this thing, which I'm calling b sub n, converges. So b sub n converges. But what do I know? I know that a sub n is always less than b sub n. We just showed that it's always less than b sub n, right? And let's go back. If b sub n is always bigger and it converges, and a sub n is always smaller, then what does a sub n have to do by the comparison test? Okay, so by the comparison, this is b sub n and this is a sub n. Isn't a sub n then sandwiched in between our limit and b sub n, right? Or 0 in this case. Okay. Yeah, this is it's sandwiched. Okay. So by the comparison test, okay, by the comparison test, the summation of n equals 1 to infinity of, okay, by Peirce series, p equals 2. Okay, by the comparison test, this thing, okay, 5 over 2n squared plus 4n plus 3 is convergent. Boom. Nice. Okay, let's talk about the limit comparison test. Limit comparison test. Okay, limit comparison test. Okay, nice. Okay. Sorry. Okay, limit comparison test. Suppose that the summation of a sub n and the summation of b sub n are series with positive terms. Okay. Then positive terms, period. If the limit as n goes to infinity of a sub n over b sub n is equal to a constant, okay, equals c greater than 0, where c greater than 0 is a positive constant. Okay. Then either both series converge or both diverge. Cool. Okay. So they either both converge or they both diverge. Huh. Okay. So let's look at let's look at what we did on the last one, right? So what did we said a sub n was equal to 5 over 2n squared plus 4n plus 3. B sub n, which we were comparing it to, which we know converge. Okay, we know that this thing converges. 5 halves 5 over 2n squared, right? And so we take the limit as n goes to infinity of 5 over, this is a sub n over b sub n. Let me go plug that in, a sub n over b sub n, which is 5 over 2n squared plus 4n plus 3, all over 5 over 2n squared. Okay, so let's just flip these over. The 5's cancel out, right? And what are we left with? We're left with 2n squared over 2n squared plus 4n plus 3. Okay, we want to take the limit of this thing. This is a limit, okay, as n goes to infinity. This is a limit as n goes to infinity. Okay, and so well, we could do L'Hopital's rule on this thing if we really wanted to. Okay, we could say that this is going to be 4n over 4n plus 4. Okay, limit as n goes to infinity. And then we can do L'Hopital's again. And this becomes the limit as n goes to infinity of 4 over 4, which is 1. Since that's a constant, what do I know? I knew that since b sub n converges, then a sub n also converges. Oh, okay. So a little bit of algebra, a little bit of L'Hopital's rule, and we're there. Okay. Okay, let's see what we can do with this guy here. Okay, let's look at our test. Let's run through our tests that we know so far. What are the tests? What are some of the tests that we've worked with so far? I believe there are 6 of them that we have looked at so far. Let's do a little review here. Just a tiny little review before we finish up today. Okay, what? Geometric. Okay, there you go. Geometric. So geometric series test. Okay, what else? What else do we have? Divergence test. Okay, there you go. You guys are doing this in order. That's kind of nice. Divergence test. Okay, what else do we have? The integral test. Okay, integral test. Okay, what else? What else do we get? The P-series test. There you go. P series test. Okay, what else do we get? Okay, the comparison test. Yeah, the comparison test. And what else did we get? Anybody? The limit comparison. There we go. The limit comparison test. Limit comparison test. Okay, so geometric series test. Can I test for convergence? Can I test for convergence? Is that a convergence test or a divergence test? Can I test? Well, I can do both, right? So this can tell me if it converges, or it could tell me if it diverges. Does that make sense? The divergence test, this can only tell me if it diverges. What about the integral test? Does that tell me if it converges or diverges? It tells me both. It tells me if it converges. If the integral converges, then the series converges. If the interval diverges, then the interval diverges. What about the p-series test? P-series test will tell me if something converges, right, for p greater than 1.
Sorry, I missed that. Could you say it again, please?
I'm not saying theory, I'm saying series. Okay?
I don't know what that means.
So,
if you like, I can search the web
hey,
for.
girl.
I'm not saying Siri, I'm saying Siri.
Yeah, stop it. Okay? STFU. Look that up, Siri. Tell me what that means. Okay. I'm basically in technological hell today. This is I need 3 days off just to recoup from my technology trying to ruin my life. Okay. Okay, comparison test or p-series test, that also tells me if it converges or diverges. Okay, that's good. Okay, comparison test. If certain criteria are met, then it tells me it converges or diverges. I want to talk about that for a second though. This one is tricky. This one is tricky. I'm going to put a little star by number 5 because I think number 5 is actually the hardest to work with. Okay, I think it's the hardest to work with because it doesn't always work. It doesn't always work. We'll get to why that is in a minute. This does tell me if it converges or diverges, but it's under special. Okay, diverges. Okay, but it's under special conditions. The limit comparison test, yes, that tells me if it converges. If they're both convergent, then I get a constant. Converges. If they're both convergent, then I get a constant. If they're both divergent, I get a constant. Okay. Okay, but what about the comparison test? The comparison test does not always work. What happens if B sub n, okay, is convergent, but, okay, B sub n is convergent, but A sub n is bigger than B sub n? What then? Well, then I chose wrong. Okay, then look at, if B sub n is convergent, but A sub n is bigger than B sub n, A sub n is bigger than B sub n, well, what do I know about A sub n? Nothing. Okay, it has to be less than. If the inequality is backwards, then we chose. Okay, maybe I should reverse these. Let me reverse these. Keep it consistent with the notes. Okay, if A sub n is convergent, A sub n is convergent, but B sub n is greater than A sub n, right? B sub n is greater than A sub n. Okay, then what? Then we chose B sub n wrong. okay, then it tells me nothing. Tells me nothing. Okay, then we chose B sub n wrong. There's no conclusion here. Okay. Also, if we get divergent, okay, say that B sub n is divergent, right? So say that B sub n is divergent, right? We know B sub n is divergent, but A sub n is less than B sub n. Well, again, what does that tell me? It tells me nothing. It tells me absolutely nothing. It's in the wrong order. It's in the wrong order. So we have to choose. Okay, we chose A sub n wrong. We chose A sub n wrong. We chose wrong. Okay, we chose wrong. So we have to find something that's smaller. Okay. Or sorry, we have to find something that's smaller for our for what we're comparing against if we want convergence. We have to find something that's bigger for divergence. But if we get the inequalities mixed up, we chose wrong. So it's very particular on how we use it. Okay. Okay, so let's see what we get here. Let's do another example. Okay. So I wish I had a good example offhand for choosing wrong, but I don't. We'll see what we can come up with. Okay, test the series. Okay, the summation of the natural log of n over n. Okay, for convergence. This one looks similar. This one looks similar. Well, I think we did an integral on this one before, right? Okay, what is this thing? I think this thing diverges. Didn't we already do this one? I thought we already did this one. Okay, in a previous life. Didn't we do an ln of n of there we go, here we go. Yeah. What do we did the integral test on this thing. Okay, determine if this thing, it's number 3, if this thing converges or diverges. And we said, oh, by the integral test, it diverged. Boom. Okay, done. We're done with our problem. I'm just kidding. Let's do a comparison test on this one. We should get divergence. If we don't get divergence, then we messed up, or we chose wrong for the value that we're comparing against. Okay. So, yeah. Let's test this series. Okay, let's test this. Okay, so I'm going to say that A sub n is equal to the natural log of n over n. Okay, A sub n is equal to the natural log of n over n. Okay, so what do I want to compare this to? What do I want to compare this to? Any ideas? Well, let's choose wrong first. Let's choose wrong. Okay, let's choose wrong first. Okay, so how can we choose wrong first? Well, let's say that B sub n is equal to 1 over n squared. Okay, I want to compare it to 1 over n squared. Because I know that this guy's convergent, right? That guy converges. Okay. So we know that guy converges. B sub n converges. Nice. Nice. So what does 1 over n squared do? Well, it goes like this. And it converges, right? It converges. The sum of it. The sum of this thing converges. Sum of these. Okay, so B sub n is here. B sub n converges. I know that. But what also do I know? If I compare 1 over n squared with natural log of n over n, what's the problem here? Well, the problem is the way that the inequality goes. This is smaller. Okay, A sub n is smaller. No. b sub n is smaller than a sub n, and I really want b sub n to be bigger, okay, than a sub n. If I wanted to squeeze this, right? If I wanted to squeeze it, wouldn't a sub n always have to be smaller? If I wanted to squeeze that to converge, a sub n would have to be smaller, but it's not. It goes backwards. This is the wrong direction, so we chose wrong. We chose wrong. Wrong choice, amigo. Okay, we chose wrong for this one. Okay, we cannot compare it. You cannot compare it to 1 over n squared. Okay, I could compare 1 over n cubed to 1 over n squared, because there the inequality goes the right way. I want b sub n to be bigger. B sub n bigger. B sub n to be bigger. I don't want b sub n to be smaller. That doesn't serve me any purpose. Okay, so this doesn't work. Okay, so go back to the drawing board. And we say, okay, what do we want to compare the natural log of n over n to? Oh, wait a second. I have an idea. What about we compare it to 1 over n? Why? Because I know what this thing does. What does that thing do? That thing diverges, right? Oh, okay. That thing diverges. Well, what do I know about the relationship between the two of these? Natural log n over n compared to 1 over n. Well, this thing's always bigger or equal to, right? Okay. Okay. For, and I'm going to put a little caveat in this, for n greater than 3. N greater than 3. It kind of has issues in the beginning, but eventually it as long as we start at 3 or above, we're good. Okay, so this, okay, is b sub n, this is a sub n, and b sub n diverges. Okay, and so we get a divergent series, okay, that diverges when, okay, this thing is bigger than it, then it must also diverge, right? So if b sub n is smaller and a sub n is bigger and it diverges, then we can use the comparison test. Okay, now why does this thing diverge? Well, let's write out the first few terms of these. Okay, b sub n. B sub n, okay, a sub n is going to be natural log of 1 over 1, okay, plus natural log 2 over 2, plus natural log 3 over 3, plus natural log 4 over 4, plus natural log 5 over 5, plus dot, 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 right? Okay. Okay. Interesting. Okay, and then this is just 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, right? Okay, well, for this thing, a sub n, I'm gonna just write the values above them. What this is. This is 0. So that doesn't quite work. 0 is bigger than 1. Okay, so 0 is smaller than 1. So that doesn't work for the first for these terms. So when n equals 1, this fails. Okay, what about this one here? This is 0.69 over 2. That's the natural log of 2, which is about 0.35. Okay, and so what's 1/2? 1/2 is 0.5. So this is 1. This is a 0.5. So again, this is not bigger. It's not bigger. Okay. So it's looking like it's not working. Let's go to natural log of 3. Well, what's natural log of 3? Natural log of 3, okay, is 1. Oh, look at this. This is 1.09 over 3. This is promising. Okay. Divide that by 3, and I get 0.36. So this thing here is 0.36. And what's 1/3? Well, that's 0.33. Aha. It's looking good here. It's looking good. What about natural log of 4? Well, because the natural log of 4, okay, starts going bigger than 1. Okay, all these natural logs are then bigger than 1 after this. Then this is bigger and this is smaller for all successive terms. Okay, if you did natural log of 4, right, natural log of 4, you would get 1.39. Okay, and so after 3, we can definitely see, boom, we could even say after 2, after 2, they are all bigger. Okay, A sub n's are all bigger after 2. So what do? We just say, hey, you know what? Forget about the first 2 terms. Start at 3 to infinity, right? So just go from 3 to infinity, n equals 3 to infinity. But we can still use the comparison test. We just start at 3. Okay, so we're just going to say, does this converge or diverge? Well, since, okay, summation of n equals 3 to infinity of 1 over n diverges, it still diverges, and the natural log of n over n is greater than or equal to 1 over n for all n greater than 2, okay, then we can say that n equals 3 to infinity of the natural log of n over n also diverges. Thus, if I just add on the first 2 terms, well, if I add on the first 2 terms, if I get a divergent sequence and I add on another 0.35 to the divergent sequence, I still get a divergent sequence. It doesn't matter that I add on the first 2 terms or not. It's still going to diverge. Okay, it doesn't change that I'm adding bigger and bigger numbers as I go along. Okay, so thus the summation of n equals 1 to infinity, natural log n over n also diverges by the comparison test. Comparison test. Okay, by the comparison test. Nice. Nice. Okay, last example for today. It's good because I ran out of paper. Okay, number 3. Okay, test the series. Test the series. Okay, summation n equals 1 to infinity. Okay, so what do you guys want? Sorry. Did he freeze? No, I didn't freeze. Sorry. My brain froze. But it's all good. Okay, sorry. I got distracted by a text. My bad. Okay, one of my bosses was texting me. I'm like, oh crap, what now? Okay, so text the series. Okay, test the series. N equals 1 to infinity. I should have just said yes. I froze, but I'm too honest for that. Okay, 1 over 2 to the n minus 1. Okay, for convergence. Oh no, is this thing going to converge or what? For convergence. Okay. So what are we going to do here? Well, I'd like to test something else for convergence. Well, let's look at this guy, n equals 1 to infinity of 1 over 2 to the nth without the minus 1, right? Without the minus 1. Okay. Yeah. Okay. And so, again, this goes the wrong direction, though. Well, that kind of sucks. Why does this go the wrong direction? Because this thing, I want to, well, let's get to how this thing behaves first, and then we're going to see why it goes the wrong direction. But then we're going to see that we can actually do a workaround here. Okay, that makes sense. So let's see, what is this thing going to do? Well, is this thing going to converge or diverge? Converge? Diverge. Is this thing going to converge or diverge? Do you think? What do you think is going to happen here? Well, let's do the nth term test. Nth term test. Is this, if this thing doesn't go to 0, then I know it's going to diverge, right? Okay, let's do the nth term test real quick. So the limit as n goes to infinity of 1 over 2 to the nth is equal to 0. Ah, that goes to 0. So what does that mean? That means that it it's inconclusive, right? It's inconclusive. It could converge, it could also diverge. Okay, we just don't know that it does definitely diverge. It's inconclusive. Okay, so that kind of sucks. Doesn't tell us anything. Okay, we just know that it does go to 0. The nth term does go to 0, so that's inconclusive. Okay, what's another test that we could use? Any other test that we could use? It's not a p-series, right? It's not a p-series. P-series. Why is it not a p-series? Okay, because...
To allow web search intent, you'll need to change settings on your device.
Stop. I'm shutting you off. I'm actually turning my phone off. Okay, you have an off button, which most women don't have an off button, but you, fortunately, have an off button. It's also throwing you, okay, into the other room. See you later. Bye-bye. Just that's like virtual spousal abuse, I guess. I threw her into the living room. So go away, Siri. Stop ruining my life. Okay, so the p-series, okay, does it work? No, because it's 1 over n to the p. It's not, this would have to be 2n squared, and we've got 1 over 2 to the n, right? It's backwards. This is an exponential, not a polynomial. So that doesn't work either. P-series doesn't work, and term test doesn't work. What else we got in our bag of tricks? How about the integral test? Okay, geometric. Is it geometric? Ooh, I like geometric. Let's do geometric here. Is it geometric? Geometric? Okay, is it geometric? Well, what's 1 over 2 to the n? Isn't that the same as 1 over 2 to the nth? And wouldn't this be a right? Wouldn't this be a common ratio? Common ratio of 1/2, which is less than 1. So by the geometric series test, okay, by the geometric series test, this thing is what? Yeah. Okay, very good, Victor. It is convergent. Okay, it is convergent. This thing is convergent. Ah, nice, 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 baby. Okay, from Vanilla Ice, who actually got sued for that song because he stole it from someone else. Stole it from Queen, the intro, I think, on that one. Anyway, okay. Queen. It wasn't Queen. It was David Bowie and uh, the guy from Queen. Anyway, okay. So anyway, it's nice. So we know that this is convergent. Okay, so that's a starting place at least. N equals 1 to infinity of 1 over 2 to the n is convergent. Nice. Great. Great. We have something that's convergent. And we want to know, okay, n equals 1 to infinity of 1 over 2 to the n minus 1, right? Okay, so let's try the basic comparison test. Let's say that a sub n is equal to 1 over 2 to the n minus 1, and b sub n, which we know is convergent, is 1 over 2 to the n. This guy we know is convergent. So how do these two compare to each other? We know b sub n is convergent. If I can get a sub n to be smaller, then I'm golden, right? So b sub n we know is convergent. Okay, then if we just get a sub n to be smaller, then we're good. Then we can just use comparison test here. 2 to the n minus 1. How does that compare to 1 over 2 to the n? How does that compare to 1 over 2 to the n? Any ideas? Which one's bigger, which one's smaller? Which one's bigger, which one's smaller? This, I'm taking 1 and I'm dividing by a smaller number. Oh, that sucks. Why does that suck? Why does that suck? That sucks because it's the wrong direction. If this was only a plus, then I would win. But it's not, it's a minus, and so I get it's the wrong direction. A sub n is always slightly bigger. It's always slightly bigger than b sub n. So I'm done, right? I'm done. Or I have to choose what I'm going to compare it against. No, don't do that, okay? If you choose wrong, it's okay if your choice is close. Why? Because the limit comparison test says what? Limit comparison test says that even if your chooser is a little bit off, it's still okay. Because the limit as n goes to infinity of a sub n over b sub n, as long as that's a constant, then we're good. Then we're good. Why? Then we know that if this guy's convergent, then this guy's convergent. Ah, okay, so let's try that. So the limit as n goes to infinity of 1 over 2 to the n minus 1 all over 1 over 2 to the n is equal to the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. I'm going to divide both top and bottom by 2 to the n. Okay, so this is going to be equal to, okay, and I can do that because 2 to the n is never 0. Okay, that's good. Just a little side note. Okay, so this is going to be 1 over 1 minus 1 over 2 to the n, and that's a limit as n goes to infinity. Nice, nice, nice. Okay, and then this thing goes to 0 because 2 to the infinity is just infinity. 1 over infinity is 0. That goes to 0. And so this just becomes the limit as n goes to infinity of 1 over 1, which is 1. And that's a constant. So what does that tell me? That tells me that since b sub n is convergent, a sub n is also convergent. Ah, nice. Nice. So we didn't need the basic comparison test. It didn't work anyway. And so we could go to the limit comparison test, and we got this to be a constant. And so therefore, by the limit comparison test with, I'll say b sub n, the summation of b sub n equaling the summation of 1 over 2 to the n, by the limit comparison test using, I'll say using this, then using this, which is convergent, which is proven to be convergent, okay, then the summation as n equals 1 to infinity of 1 over 2 to the n minus 1 is also convergent. Okay, so do you see how when you try something and it doesn't work, there are still more tools out there for you to try? Okay, and again, we're going to end up with 10 tools, 10 of these crazy tools. We already covered 6 of them, and that's enough. That's enough. Now, Fady, if you still want me to do that one problem, I'll stick around and do that one problem. Okay, but the notes for today is done. Okay, I'll see you guys on Monday. Yes, yay, yes. I'm going to call Microsoft and send them back their stupid Surface. And I'm divorcing Siri. We're getting divorced. It's very sad. Okay. It's always the iPads that suffer in the divorce. The little guys. The little iPod Nanos. It's very sad. I'm gonna stop my share now. Okay. Fady didn't stick around, so I'm gonna say adios to everybody else. Okay, see you later, Victor. Talk to you later. Yeah, I'll post the videos. Yeah, they have to download it. It takes like 3 hours for them to download it. I need more technology, but I'm poor and I can't afford it. So it just kind of sucks. I need a much faster processor to download all these videos. But I don't know. Maybe I could start like sewing together masks and distributing them to people for like $1 a piece. And be like, help me help you. Help me teach my students. I need a much faster PC. Yeah. See you guys later. Bye-bye. Bye-bye.